definitions? So again, there is a question on application of these parameters. So application of any parameters is the same. It is to get a compact representation of a complicated circuit. You could have hundreds of components in this, but let's say only 2 ports are exposed, that is 2 terminal pairs are exposed to you. You can describe the behavior of this entire complicated circuit with 4 parameters. Okay. And you could choose Y or Z or H parameters, or we'll see another one which is known as G parameters. Okay. Like I said a few times before, which one you choose depends on convenience. Okay. Now traditionally, there are components known as bipolar junction transistors which are used to make amplifiers. So those were described with H parameters. Okay. And there is a question of why it is hybrid. Hybrid, see, if you look at Y parameters, all the Y parameters have conductances. They have dimensions of conductances. And Z parameters, all of them have dimensions of resistance. Then these H parameters, the dimensions are all mixed up. One of them is a resistance, one of them is a conductance, and 2 of them have no dimensions. Okay, so that's why it's called hybrid. And his last question is there any circuit element? I am not sure of what this question means. Where are the circuit elements? So again, I would encourage you to calculate H parameters of this network. Okay, it's the same network I had earlier, so I'm not going to go through this. Please try to do this as an exercise, and if you run into any difficulty, please let me know in the next lecture. Okay. Now finally, we can also express here, we have expressed V1 and I2 in terms of I1 and V2. We can also express I1 and V2 in terms of V1 and I2. And in this case, we think of a voltage being applied here and a current being applied to port 2. Okay, and we measure current I1 and voltage V2. Okay. So very quickly, please give me the dimensions of G11, G12, G21 and G22. What are the dimensions of G11? Clearly, G11 multiplies the voltage to give a current, so it has dimensions of conductance or units of Siemens. Okay. What about G12? G12 is clearly dimensionless. It multiplies a current to give a current. And G21? It is also unitless. Okay, it multiplies a voltage to give a voltage. And finally, G22? G22 multiplies a voltage to, I think I made a typo while writing. This is I2. G22 multiplies a current to give a voltage. So this has dimensions of resistance. Okay. So this is also a hybrid. You have conductance, resistance, and dimensionless parameters. And in fact, they are the exact opposite of H parameters. Okay. So this is another set of hybrid parameters. Okay. So I won't go through this again. So you can figure out how to measure G11 and G21, how to measure G12 and G22, what you should do to port number 2 and port number 1, and so on. Okay. So I think you'll be able to do this for yourself. And also, as before, just to get some practice, calculate the G parameters of this circuit. Okay. Somebody answered that G22 will have no units. That is not correct. G22 will have units of resistance, dimensions of resistance. Okay. So why is the name G given? I have no idea. It's some historical reason. There was H and there is G. So I really don't know why G is given. It can be a little confusing because we use G for conductance as well. But this G in 2-port stands for some hybrid parameters. Okay. Now finally, we know that for a resistive network which is reciprocal, we saw that Y12 and Y21 are the same and Z12 and Z21 are the same. Okay. Now is there any such relationship for H parameters or G parameters? Okay. So just to refresh your memory, we discussed reciprocity for this case for I1 with this side short circuited, and we measured I2, and in the other case we had V2, we had this side open circuited. Okay, V2 hat and V1 hat, and there was some relationship between I2 by I1 and V1 hat by V2 hat. Okay, what was the relationship for a reciprocal network between I2 by I1 and V1 hat by V2 hat? So we derived this by putting a current on one side and a voltage on the other side. What is the relationship between I2 by I1 and V1 hat by V2 hat for a reciprocal network or a resistive network? Relationship between these two ratios for reciprocal networks. There is an answer that says both are equal. There was a slight twist. I2 by I1 equals minus V1 hat by V2 hat. If you apply Telegan's theorem and calculate the reciprocity relationship, this is what you will get. Okay. So this means that for the hybrid parameters for a reciprocal network, okay, H12 will be minus H21 and G12 will be minus G21. Okay. So they are related. H12 is the effect of port 2 on port 1. H21 is the effect of port 1 on port 2. Okay. So in general, parameter 1, 2 shows the effect of port 2 on port 1. Parameter 2, 1 shows the effect of port 1 on port 2. And in a reciprocal network, these two will be related in some way. For Y parameters, the relationship is that they are equal. And for H and G parameters, they are equal and opposite of each other. Okay. Any questions about this? Okay, finally someone in the chat window commented that H11 equals Z11. Is this correct? What do participants think? Is H11 the same as Z11? So the answer is no, it's not the same, because if you think about it, V1 is H11 I1 plus H12 V2 in terms of H parameters, and V1 is also Z11 I1 plus Z12 I2. Okay, but if you look at the value of H11, it is V1 by I1 with V2 equal to 0, that is port 2 short circuited, whereas Z11 is also V1 by I1 but under different conditions with I2 equal to 0 with port 2 open circuited. Okay, so H11 is not the same as Z11. In fact, all these parameter sets, the parameters will be different from each other. Okay, although one can be derived from the other, they are not the same as each other. Okay. So I hope that is clear. There were a number of other questions asking about details on reciprocity and so on. So we went through a long discussion on that in one of the lectures. I suggest that you please go through that lecture. If you have any doubts, we can discuss that. And then there is some question asking for books on network theorems. Books like Haidt and Kemmerly or Lin and DiCarlo are good, but I will go through the books again and then give suggestions next week. Okay? Okay, thank you. I'll see you next week.
Swayam Prabha. Digital India. Educated India.
Good day to all of you. We shall continue with our discussion on design of controllers, specifically for DC-DC converters. As you recall, we have done the modeling of the DC-DC converters, and in the last few classes we have been discussing the basic principles of the controller, reviewing them in fact, and trying to understand the operations of the PID components of a controller. The PID controller is one of the most robust controllers and very popular in the industry too. And that is what we would be using for ultimately to close the loop for the DC-DC converter too. So, in the last class we had discussed, we had completed our discussion on the PID components and had just begun to look at how the P, I and D components can be implemented using op-amp. So, we had started with the integrator, and then we shall continue on towards the other components and see how we can integrate it with op-amps. Of course, if you are using a digital controller, if you are using a digital processor like a microcontroller, then you have to implement the equations, the PID equations within them. So, coming to our topic here of implementing the controller, let me again bring you back to our block diagram. You may be already knowing this block diagram, but let us write it down once again. We have Ki, the integrator portion. The integrator, I am going to write it as 1 by S. You have the Kp portion, the proportional gain, and you have Kd, the scaling for the differentiator, and I am going to write the differentiator as S. And the denominator, I am going to write it in dotted on another color as S plus A, implying that you cannot escape S plus A, even though S is the only thing that is required. So, S plus A is a pole which is very far in the frequency axis. And all these outputs are added up in this fashion. Plus, plus and plus, and the output of this goes to pulse width modulator. We will call that one as pulse width modulator PWM, and the output of that goes as the control input D to the DC-DC converter. This is the plant. The sensed output could be V naught is fed back and this is, let us say, V naught reference, V feedback, V naught feedback. or just V naught, so that you have less number of subscript to worry about. So, we had in the last class mentioned that this is the reference, it could be any reference, it could be current reference, voltage reference, depends upon what you actually want to control, Now, let us say for example, that we want to control the output voltage of the DC-DC converter. So, that is the one which is fed back, and a suitable reference for that is the one which we need to apply the desired reference. Now, this is our control structure. In brief, there are still a lot of details that we need to worry about, which we will do that as we progress. We had been trying to replace these blocks. We have been trying to replace these blocks with op amps. So, first what we did was that in the last class, we replaced the comparator portion with an op amp, a differential op amp. Let us say this is the plus and this is the minus. So, a diff amp is written in this form. You can refer to any book on op amps, and you can get a host of op amp circuit ideas from them. So, this is the positive is connected there, the negative is connected to V naught. So, what we shall do is connect it in this fashion. Now, all these resistances are for now, let us maintain it as same values. So, you will get an error E, which is nothing but V naught ref minus V naught. This E equals V naught ref minus V naught into R by R, but as the values of resistance are all equal, they actually cancel out and this would go. So, it is just V naught ref minus V naught. Okay. So, this is the first part, comparison. I am going to remove this so that we do not clutter up the board. And next, we had replaced the integrator portion with op amps. So, let me do that for you now. Recall, go back to the circuit that we discussed in the last class. It involved two op amps, one for integrating and another for setting the gain. But you can reduce the number of op amps, but right now do not bother too much about the number of op amps. We shall just try to replace the equations with op amps. So, this is an integrator. Let us say this is R I C I. You can add one more gain stage here if needed, and that is what we had included in the last class, minus and plus. So, this RI1 and RI2 would give not only gain, but also the inversion. This portion gives additional gain plus inversion. Okay. So, you have 2 degrees basically setting the gain of this stage and setting the integration gain at of this stage. You have an inversion here, you have one more inversion here. So, from here to here there is no inversion. Or you could remove this stage and just set the gain, integrator gain, by choosing properly the value of this and this. So, let us probably make things simpler. For now, let me remove this stage, one set of reduction. So, we have it like this. What is the output here? You have E as the input, you have E as the input here, and let me call it as the integrator V naught I, output of the integrator. So, V naught I is, now there is an inversion, we will keep it as minus 1 by R I C I integral of E dt. This is the equation of the integrator output. So, this essentially is the gain K I and the integration E. So, this would be your K I in your. So, properly choose R I C I product to achieve the value of the desired gain scaling. So, let me again wipe out this portion so that we do not clutter the board, and look at the next portion. The next portion of course is K P. Remember that we now have an inversion at this point. We will take care of this inversion while doing the summing. Okay. So, we will give inversion to all these and then take care by giving a summing point at the summing point. Now, this portion, the proportional or the gain portion, can be addressed by putting one single op amp here. We can introduce an op amp here, minus, plus, and gain. This is an inverting amplifier, recall from your op amp classes. So, if this is RF and RP, we have the input as E here and output as V naught proportional.